Good afternoon to you. Good afternoon to all of you, Putala. Manufacturing, food process, and IM for today. Environmental management and clean production session. On the 15th March 2021. Yeah, good afternoon to you, Putala again. So I can notice that the food process technology students are here, even though in less numbers. IM students are here, but manufacturing seems the presence looks quite weak, but I believe I have sent the invitation to all the three batches at the same time. Okay. Attending is good and it is encouraging for you and me both. And also, this is the time schedule for us to be together and share the knowledge. So, listening to the videos is secondary. After attending this proper lecture session, and that's why. So, that is very important. Yeah. Today, this is our plan. Okay. Even that day with the weekend students, I have shared 12 principles of green. That sharing with the B2 students, 12 principles of green engineering is a simple briefing only. So I didn't have that much of time to share with you, even though I share that video with you. So since it is very important to learn about this, and this consider the important and the prior knowledge, so we thought of looking into this as well. So our lesson out of this is to understand this, and then the importance of practicing. Yeah, we have to practice this 12 principles. Where? On the jobs, in the designs, manufacturing, trading, services, okay, industries, yeah, even in day-to-day activities and even in decision making, okay, yeah. On the job, in the designs, decision making, and all, which means this is, I would say, very important, and everything is summarized in the sense, if you think of environmental management and cleaner production, the scope, okay, this covers the most. This covers the most. So we are going to discuss this, and every time in all the exam papers, you will see a question out of these 12 principles of green engineering. Okay, so this is one of the plans for our knowledge sharing today. So other than that, I just highlight here the 3M PPP program. 3M PPP program. So we have not discussed this with any of the batches. So we should look into this. Okay. PPP means, write down, PPP means when it comes to environmental considerations in manufacturing, the first P is pollution. Second P is prevention. Okay. First P is pollution. Second P is prevention. Third P is pace. Pace means it has some financial advantage. Pollution, prevention, pace. So 3M, because of the prevention of pollution, even they save annually, once they implemented this, they save annually, I think, over $600 million, this company. $600 million means, when it comes to rupees, so you can see it's around 120 billion rupees. It's massive money for a company. Okay, 120, oh yes, 120 billion. So the lesson we are expecting to learn, reducing impact of manufacturing industry on environment. So we have to receive this awareness, okay, the sense of this as a basic knowledge. So item 3 is about VOC, greenhouse gases and greenhouse effects. I think the video I sent to you, that's a knowledge sharing with B2. So I have discussed this very well, but not VOC. So today maybe we are going to discuss VOC effects. Okay, VOC effects. So these are the things we planned. We will try our best to cover everything, but even if not covered, we may need to look for another session, or else you have to look for the knowledge resources to gain the knowledge, no matter I share it or not, because these are important. Okay, that's right. So we will look into the 12 principles of green engineering now. Okay, I would say that. So I just leave our lesson. Initially, this 12 principles initially applied for chemical industries. Okay, initially applied for chemical industries. That's how it began. Later, this is popularly used in this 12, okay, later applied for other industries, and even now you can interpret, okay, even now these 12 principles can be interpreted for other sectors as well, which means this knowledge has a universal nature when it comes to the application. Okay, this knowledge has a universal nature. Okay, when it comes to applications. Okay, when it comes to applications. Okay, that's why. So this is considered quite important knowledge. Okay, quite important knowledge. I came to know this, okay, around 15 years back. Not to say came to know. I have started using this around 15 years back. Yes. When it comes to designs, manufacturing, and decision making, and even in developments, product developments and research and developments. So in 2008 I have started, now it is 2021. Okay, so it's almost 13 years. But your case, at your very young age, you are going to learn this. And I'm very sure that even in the industries, I just checked with B2 students, they are from the industry. They have never heard about these 12 principles. Means in their jobs, when it comes to green engineering practices, their principle base is not strong, and their coverage is, or the scope of coverage, this environmental attention is not complete. Okay, but your case, I would say you are lucky enough to come to know about this valuable knowledge at such early ages. Okay, so let me share with you some internet contents, maybe some internet contents. Let's see. Oh, this one. Give me a second. I'm going to Google, okay, this 12 principles of green engineering. 12 principles of green engineering. So you can browse this. Okay, green engineering. See. 285 million results. Okay, you can see here, I think I'm sharing you the screen. Okay, you can see here, see, 285 million results in 0.54 seconds. We may not know about 12 principles, but the world knows this. Not only the world knows about this, they apply this knowledge. Okay, they apply this knowledge. So I would say it is so popular and it is so complete. Okay, and it is just 12 principles, but it completes the environmental management when it comes to engineering, designs, decision making, and all. Yes. So that is very, very, very important. Okay. So I'm going to open up this, what this says. Maybe instead of open up, let me copy this. Yeah. Because I'm using the reference here. Okay. 12 principles. Give me a second, Buddha. Yeah, Buddha. Okay. So let me copy this because this is American Chemical Society website. It's mentioning about this. So let me share this. On your slides. New slide. I copy this. This is about 12 principles of green engineering. Let's say what? This American Chemical Society says about this. Okay. Maximize efficiency. This is very important for, yeah, let me share that. Yeah, I'm sharing. Yeah, good. Yeah. Maximize efficiency. Products, process, and system should be designed to maximize mass, energy, space, and time efficiencies. Later, you can look into this. Later, you can look into this. about maximizing efficiency. Product efficiency, process efficiency, and system efficiency. Yes. Okay. So mass efficiency, energy efficiency, space efficiency, time efficiency. Okay, everything about efficiency. This is about efficiencies. Okay, later I'm going to share with you. Okay, later I'm going to share with you this. Yes. So the word efficiency, I think we have shared this if I'm not mistaken. So to improve or to maximize the mass efficiency. What is mass efficiency? Using of minimum masses, okay, producing the maximum. So minimize waste. You can see a lot of aspects there. Energy efficiency, minimize energy wastes, and also maximize energy usage. Space, also the same. Space is very important, you know. Space efficiency is very important. Imagine the smartphone you are having now, not to say smartphone, even the normal phone, okay? Okay, not a touch phone, even a normal phone. In the very beginning, this normal phone, it is something like a brick in size. Gadulaga size. Not the smartphone, but this phone with the press buttons, a brick in size. The battery it needs is separately powered battery. Okay, and there are other accessories. So when you have to have this mobile solution, you need a briefcase. Okay, you don't believe, but even I have used this. Yeah, that is in 1991. See now, that is 30 years or 40 years back. So 30 years back. So now it simply is a very small piece you are holding in your palm. See the space efficiency. Nanotechnologies, also about space efficiency. Time efficiency is very important. So you will understand this later a lot. Okay, so improving, maximizing mass, energy, space, and time efficiencies. Okay, so accordingly, we have to design the products, we have to design the process, and also there are systems. System in the sense, if you think of your refrigerator, within that is a refrigeration system. Okay. In the manufacturing plant of this refrigerator, okay, let's say Singer or maybe LG plant, it's a manufacturing system, okay, or a process system. So systems can be even with the products, even with the manufacturing processes, even with the operations. Let's say the supply system, bringing in raw materials, producing this, store this, transport for the showrooms, and again the logistics systems. So we can see a lot of varieties of systems. Okay, so those should be designed to maximize the efficiencies of mass, energy, space, and time. And 12 principles of green engineering is for this. Okay, that's the point. So we are looking into one by one afterward. Okay, we are looking into one by one afterward. 12 principles. So the 12 principles of green engineering, you can see the 12 principles I got here. I'm going to discuss it. And this is from American Chemical Society, ACS. Okay, American Chemical Society. So the contributors are here 1, 2, 3. Okay, 2%. Okay, should be from the chemical engineering side, if I'm not mistaken. Yes. So this is Environmental Science and Technology Journal paper. They published this in 2003. Not that old. Okay, not that old. So this is very important. Okay, now I'm going to discuss one by one. I'm going to discuss one by one. So discussing the point is, if you understand this, or if you have even a little understanding of this 12 principles of green engineering, okay, even if you have a little understanding now, one day you will understand this to the fullest. So that is the point. That's the point. So try to understand at your best now. Okay, at least you have some training exposures. You underwent training in the industries and all. So try to relate these 12 principles somehow for this. One. Okay. The first principle. And there is order 1 to 12. So this is the first principle. Number 2 is the second principle. And so on. Okay. See, 1 is the first principle, 2 is the second principle, 3 is the third principle, 4 is the fourth principle, number 5 is the fifth one. And here you have to use the same wordings. Don't change it. Okay? So, but we have to understand. So, first principle, durability rather than emo. So, instead of that, you cannot try different things. Okay? First principle is first principle. Okay? Second one is the second one. So, the same wording should be there. So that's how you should respect the principles. Okay. So what is the first principle? It is durability rather than immortality. But you have to understand this beyond words. Okay. So this can be explained in different ways. Okay. This can be explained in different ways. Okay, this can be explained in different ways. That's true. So, but the first principle is this. Yeah. How to understand this? Two keywords. Durability. Other keyword, immortality. Okay. Durability means long lasting, but one day this will be no more. But it's durable. Okay. So maybe 10 years. Immortality means maybe you can use this for generations. Same like earlier example, the machines, sewing machines, like Singer machines. So mother used it, then passed to the daughter, then to the granddaughters. So you can say that kind of machines. Okay. So used for generations to generation. Okay. Even no much maintenance. So it is something like immortal. Amaraniya is the Sinhala word for that. Immortal. Means it is not decaying. It is not decaying. Even after a few generations, still it's the same. Means it's too long. The durability is too long. So why asked to do the durable, consider the durability instead of immortality? Why? Yeah. So, and this is a design goal. Give me a second. Okay, Bhutan. So should be a design goal. Okay. Yes. Targeted durability. Okay. Not the immortality. Means, let's say, if you are making a car or developing a car, let's say example. If you are developing a car, let's say, or let's say you are developing a ballpoint pen. Ballpoint pen. So this is made of plastic or whatever. You are putting the carbon stick inside. That's it. Okay. So maybe after finishing this carbon stick, you may not be using it again. Okay. But just to use this carbon stick, if you make this pen with valuable, long-lasting material, okay, with high precisions, okay, with high precision. Let's say carbon stick may be 1 month use, okay. You are designing this for 10 years use. There is no match. That is one thing. You may think that you can refill this. Fine, you can refill this. But maybe if this is designed for 20, 30 years, surely this will be out of fashion one way. And the better solutions may come before this being expired. Then what happens? You may intend to throw this away as trash. Then creating or generating a waste by right that should not be a waste. Okay, that's why when it comes to design, see, if you are designing a car nowadays, so let's say a smartphone. Okay, let's say smartphone. So maybe every year or once in 6 months. Okay, these smartphones. So these phones may be, the casing all may be aluminum or plastic, maybe. Not carbon fiber like expensive ones. Okay. So you know that this one, if you are going to develop this cell phone or the smartphone or this touchpad phone, okay, or even the keypad phones, to last for generations, what happens? So what happens is that you miss the opportunity of using the latest ones, updated technology ones, because this is designed for generations. And sure, this will be expensive because when it's more durable, the price is very high. Material used is high quality. Okay, so you are keeping high price, outdated, okay, piece, and all the new ones are passing, and you are keeping it because it is high price. It is high price. That's why. So design for immortality means for the to use for generations is, that is not the way. Even you can see this iPads, the first generation. It's a wonderful design. It came in the mid of 2000. Even I bought one around 2009 or 8 maybe. But still it's with us. It looks very good. It's never becoming outdated, the design and all, but the application's all outdated. It may have even no antique value, but just left it. All forget. But those days it is expensive, consider very expensive. More pricier than a computer. Yeah. So even the Apple design happened to be that way. So, but now they optimize the materials and all, but superb quality. We should support Apple because the Apple founder Steve Jobs he's a great person. So we can support his products. That is okay. Okay. Let's say if you are going to design a cloth or a shirt or a blouse or a frock, if you design it for 10 years, maybe expensive materials, all expensive. Yes, even put into laundry, the quality remains easily exceeding 5 years. So who is going to keep this for 5 years? So that's why. So you are using expensive, durable material to make it long last, but you are not supposed to use it that long. Waste of materials. And the more material, may be waste of energy as well. Okay, that's why. So immortal designs means designing to last long for generations. It is not a design goal, because even that would be very pricey, expensive. Others coming with moderate durability, less price, very nice quality. Your one is maybe generations can be used, high price. Maybe in 5 months' time this will be outdated and you don't know what to do with your stocks. Okay, I think you can relate it now. Okay, you can relate it now for the applications. So designing is something like that. So balancing the cost, the process, okay, cost for the process, raw material and all for the application, to make it last long for reasonable and optimal time duration. That is very important. The electronics nowadays is outdating very fast. Today manufacturing in 6 months' time is outdated. And most of the Chinese products people are bringing here, I believe those are outdated ones. Yeah, even those are not designed and manufactured for that long lasting, but before putting into the market, those become outdated. That's why people in China, low price, fast moving, okay? So sell in the market. In 3 months' time, another product. Low price, fast moving, sell in the market. So shorter life cycles, that is not very good. That is not very good. So there should be a targeted durability, but it cannot be that 3 months like short maybe. Okay. Also, it cannot be 3 years long lasting, because even LEDs, electronics, the efficiency is all. Maybe in every 5-6 months the technology updates, the design updates. That's why. Now you can imagine in our houses, some fridges are 20 years old. maybe 30 years old, 10 years old. If you have a 30 years old fridge, your electricity bill will be very high. If can be replaced with a new one, in 1 year time, saving electricity bill saves the, saving electricity bill returns the cost of your new appliance. That's how it is. So always the technology evolves that fast. So designing, you must have a targeted durability, reasonable one. Not so short, but of course, it should have reasonable, optimal, long lasting. Beyond that, I think spending money for that is not worth maybe. That's why. So this is one of the some of the examples we are considering for this. Okay, targeted durability keywords. So when you do a design for manufacturing, so this is one of your considerations. How long should this last? Okay, car maybe 5 years. Under the tip-top condition is 5 years. After that, even we are receiving maybe refurbished one. Once refurbished, maybe another 5 years. So 10 years gone. After that, maybe using for the low-level applications, oils, it should be going for recycling. That's how it is nowadays, because engine efficiency, technologies are being changed. Okay, continuously changing. So that is the point, Pradhan. Okay, that's a point. So it is very important. So when you manufacture things, when you design things, when you buy the things, okay, considering the reasonable durability is okay, rather than you are going for the immortal life, long last for generations. That may not be necessary, of course, but there are important things. You have to build to last long for centuries. Okay, there are important things. Some structures, bridges maybe. You can see the Kalini New Bridge. If you design this for 5-10 years, I think it's a joke, you know. It should last long, at least 200-300 years. Yeah, should be that way. And the preventive maintenance is a must. Okay, that's how it is. Even a design an aircraft, manufacturing, maybe passenger aircraft, you run it for maybe 20 years. After that, it may be converted for logistic other purposes, maybe running for some time, and then this will be discontinued from the service. It is like that. So targeted durability, that is very important, because the technology is improving, is evolving that fast. Okay, so that is the reason. Okay, so you should understand this. Okay, so let me go to the second one. So first one, 4 words, durability rather than immortality. So let's say item 2. Yes, it's very nicely put into words. See? not that long no, even no sentences, few words. Okay, few words, that's it. So this is the second one. Try to understand this. Okay, try to understand this. So this is how it says. We are not going to change the wordings. Meet need, minimize access. Okay, let's say when you cook rice, let's say your house, your home, say 5% in the house. So your mother, or maybe the one who is involved in cooking, knows by experience that for this 5%, this much of rice is needed. Okay, so if you cook extra, maybe you are eating too much, or it's an excess. You may be throwing away, or you may be taking it at a later inappropriate time. So meet the need. Just cook the right amount you need. Okay? Means minimize excess. Meet need, minimize excess. Excess means you consume more, you get sick, or maybe you may be fat. Yes. Meet need, minimize excess. Same way. Let's say if you buy something, let's say if you need let's say notebook. Okay, there are books, 80 page, 120, 200, maybe 40 page or whatever. So if you need 40-page book to write, if you buy 100-page one, okay, means you are having excess. Weight wise, instead of 40, 100 means your weight is more than doubled. So it is difficult to carry, because likewise, if you have 10 books, unnecessary you are carrying over 50% waste, excess. And after writing 40, the balance, what you are going to do? Same. When you go for shopping, before buying the things, you should have a plan that I need to buy this for this purposes. Yeah. So you have to only buy that. And if you buy something extra, it is excess. We have to minimize that. Okay. So these are simple. Same when you do the designs, because this is about the engineering. So designs, or even purchasing. Let's say if you need to buy a rice cooker, or if you need to design a cooker, let's say 4-person cooker, it should be 4-person one. It cannot be 4 to 10. It's a wider range. So 10%, the rice cooker size to cater for 10%. If used for 4%, extra water maybe, extra energy loss, so extra energy. Okay, even there can be waste, maybe partly burned rice, because the bottom of the rice cooker is very wide. So for 4 person, you have to cook for 5% to compensate for the waste. Something like that. Okay. Meet the need. Meet need, minimize excess. Okay. Assembling a vehicle. So the engine requirement. So if you are doing overcapacity engines, one way it's heavier, the other way, that one maybe when you are running at low speeds with less load, this high capacity, high powered engines are performing below the efficiency levels, optimal efficiency levels. Okay, that's why. So see, that's why it says that designing for unnecessary capacity or capability, it is not good. Yes. Means one size fits for all. Okay. It's a design flaw, means it's a weakness in a design. Okay. So one way this is very good, even when it comes to the sustainable consumption and production. We can learn something out of this. Okay, we can learn something out of this. So this is the second principle of 12 principles of green engineering. The second of 12 principles. Previous one is the first. This the second means it's the second principle, not the third, also not the first one. This is the second. Okay, there is an order of learning this. Then you know apply which principle applies. Yes, first one, second one. Okay. Yeah. First one is about the durability. Second one is about the capacity, the need. Okay. Very nice guidelines. Okay. This is very important. Same. Buying a washing machine. Let's say now you have only 2%. You imagine that there may be even 10, 20 in your house and you are buying a heavy one. Instead of 5 kg, you are buying 7, 8 kg washing machine. I mean the loading weight of the clothes. So is performing under capacity. Yes. Okay, so that is not very good. And the other ways, you are buying overcapacity one means you are actually taking one product out of market which is needed for someone else, but which is not necessary for you. Okay, that is not very good. Okay, that is not very good. So that is irresponsible consumption. Okay, so nice. So try to understand, even you work in the industries for the training and all. So when you order raw material parts or anything for your jobs, okay, you know that everything is pricey and costly. So when you specify the raw materials or components or equipments, you can follow this. Okay, you can follow this. Not to buy the best one, but the suitable one. Okay. Targeted durability, if you are using it one time, okay, so you should not buy for the generations, I mean the one with extra durable ones. If you want to use 3 years or 3 months, you should buy within 1 year. 1 year durability is enough. No need extra durable ones. But of course it should perform well. That is one thing. So this is the second one. Okay. So same way, the third one. I'm explaining this because even if I explain a few, you can justify the rest. Okay? You can justify the rest. You may get some clues on the others. That's why. If I don't explain well, if you don't understand the gravity of this, if you don't feel the gravity of this, I think that is not very good. Okay, that's all. Minimize material diversity. Okay, minimize material diversity. Material diversity is okay during your usage of the equipment or anything. Let's say your smartphone. Material diversity is not a matter for you at all. But after this lifetime is gone, to recycle this, okay, inside material, you have to separate it. So let's say among plastic, there can be separate plastic variations. Then plastic also need to separate into different plastic pieces. See how tough to bring this material back to feed as a raw material of high quality. Not possible. Okay. Same way, there can be copper. If copper mixed with some other metal, let's say silver, so how to separate copper and silver if it's a mix? It is tough. It's neither copper nor silver. So silver is more valuable, but you cannot get it refined. If get it refined is costly. So it will go to the copper side. So silver used in copper side. So maybe copper may be better when mixed with silver. Who knows that even? But that cannot put into the silver side. Yes. So which means that silver deposits are limited. So that silver will not be anymore in the pure form. Means that silver is gone from the world. Understand? That's why. So when it comes to precious metals, separation is important. Sometimes there are gold being used for the electronics, for soldering, and gold can be, even silver can be. So if this gold cannot be separated, what happened? It may go with copper, then that gold is no more available to the world. It's a loss. Okay, it's a loss. So you should understand this. Same way. Okay, so this material diversity, if it is more, when it comes to recycling, the recycle efficiency may be very less. So finally, you are losing valuable raw material because it's difficult to recover. That's why material diversity in multi-component products like smartphones wristwatches, even in refrigerators, televisions, even in a fan, okay, some electronics, you can see material diversity in multi-component products, even plug tops, okay, electrical wires, so whatever, should be minimized, this diversity, to promote disassembly, means separate the materials. Once you disassemble it, material gets separated and the value remains. The copper value remains same as copper. Silver remains same as silver. Okay, that's all. So this third principle, only 3 words. So if you change this, even if you put minimize the material diversity, it is not the third principle. Minimize material diversity. Okay, third principle. So nice. First one about some planning of the design goal. How long this should last? Second one. So what is the optimal capacities you need? Second one. Third one, yes. Materials, these can be used, but the diversity should be minimal, that even after disposal, value of the materials should be retained. So nice. See? So now when you design, these are no more, before I discuss this, these are not in your thoughts even. Okay? So not only for manufacturing, food industry, when you get involved with packaging and all, okay, and when you get involved with machineries, raw materials, you can think of this, okay. And for IM students, you will be in the team of the developments, yes. Since you know about the 12 principles, you can question the team. You can put the ideas into the team. How would be the durability? How about the material diversity? How about the capacities? So why we are designing for higher capacities if we need this? Instead of higher capacities, why we do 2 separate models instead of doing 1 to fit all? Because 1 to fit all is a design mistake. Okay, that's why this knowledge is relevant for everyone. So you imagine these simple principles, once known, how valid and how valued are these? Yes, that's why. Those are really practical, feasible, useful, scientific, technical. Very nice knowledge. Okay, very nice knowledge. So you just learned this number 3, third of 12 principles. This is not neither first nor second. Okay, this is the third. Also, this is not the fourth. Same way we will look into fourth principle. Okay, so I'm explaining this in this way because with this explanation, you feel how important this. And let's say, if we can complete only few explanations, you felt the importance of whatever complete, and the balance, you know that it is equally important, and you may explore those. Yes. Complicated words, but very few words. Okay. Very few words. So this is how the fourth of the 12 principles of green engineering mentions. Inherent means naturally, by default. Okay, so it is something like inherent. So if you are going for a similar wordings, inherent, yeah. Characteristics, okay, inborn, natural, inbuilt, it is within, rather than circumstantial. Okay, means it is depends on the situation. Let's say if, okay, yeah, we will go through this. This is talk about hazardousness. Okay, so inherently should be non-hazardous. You know, hazard means it's something like dangerous, risk for the human and environment. So when you are using material and energy as inputs, and you are using the processes for this, and you are producing outputs. So this inputs, processes, and processing time, and also outputs naturally should be safe. Natural. Okay. So there cannot be any situational, okay, risks. We call accidental risks cannot be there. Inherently non-hazardous. Let's example asbestos manufacturing. Yes. It is not naturally non-hazardous, but not naturally means inherently asbestos is not non-hazardous. It is hazardous, but maybe in situations you can use asbestos in a safer way, but not 100%, but in somewhat safer ways. So that's why. So cannot be circumstantial, but should be inherent. So when it comes to steel roofing, yes, inherently safe, okay, for humans usage. Yes. So even for any situations, it may be safe. Not like asbestos. That is one example. Okay. Some products, we have the lithium-ion batteries, battery technologies. So battery technologies are very risky, you know. Battery technologies are not non-hazardous. If catch fire, you cannot control it. It keeps on until the end of this material. Can you remember one story? We saw the news item that in Anuradhapura, one gangster, his car was shot at his car, and immediately went into flames. And of course, in the news, it says that the fire brigade came and doused the fire, stopped the fire, extinguished the fire. But when you look at the car, only the steel frame is there, all gone. It's a hybrid vehicle. Okay. the battery has hazardous. So inherently it is not hazardous, but some circumstances it is dangerous. Okay, but many circumstances it is safe. Some cases it is dangerous. Yeah, same. In refrigerators, air conditioners, this R600 daylight refrigerants. You have heard the new ones. It is not naturally safe, but we created a circumstance within which usage is safe. That's why sometimes you can see refrigeration with the new refrigerant related explosions. Servicing maybe, some wrong usage maybe. Yes, that's right. So there are issues, but we will try to avoid this. Even the LP gas you are using, flammable, but you are using in controlled way. Yes. So you are making it inherently safe, but not to the fullest, because there are gasoline explosions. That's all. So you have to think about this when you do the designs, when you do the applications, when you provide the solutions. And this is about the safety and health. You can say it. Even electrical safety of appliances. Let's say example, if your iron, yeah, so all made of plastic, you handle everything plastic and only the metal plate is made of metal. So you are not touching the metal plate. So you're holding the plastic and you do the ironing. So the design inherently look safe for electric shocks and all. Yeah, even a rice cooker you can see safe, but anyway you have to take extra precautions because there can be electric accidents while using the appliances. That's why. So you have to minimize these risks and try to make it inherently safe and non-hazardous. Not circumstantially safe. Okay, inherently should be safe, not conditionally safe. Yeah, circumstantial means conditional, conditionally safe. Under these conditions, this is safe to use. Yeah. So that is circumstantial. Yeah. Under any condition, if this is safe, we call it inherently safe. Okay. So see now, in the designs, this is the fourth principle. Okay, this is the fourth principle. If you look into the flow, the first one about the targeted durability. Second one, what kind of capacities? Third one, yeah, we have to be mindful about afterlife recycling. See, the design approach, you are naturally being guided for good designs. Then fourth one, safety. See how good this knowledge is. That's why this is everything I would say, Budala. Okay, so that's why you respect this valuable knowledge, you understand this. And once you understand, I'm very sure that you are following this. Whatever solutions, let's say, sometimes you are modifying your bikes. Yes, so you can think about this. Performance, you are going to change. You are taking risks maybe, but anyway, you have some very thoughtful, not to having a fear, but have a very methodical, wise approach to minimize the risks. Okay, and that's why. So this is neither third nor fifth. This is the fourth one. You can see these principles are nicely flowing and well guided. That's why first of 12 is the first, second of 12 is the second, third of 12 is the third, and fourth of 12 is the fourth. And the 12th of 12 is the 12th. Yeah. So you can see, at least if you understand the first 6, maybe you will be in very good shape in your approaches. Understand? And whatever the machines you developing, maybe agriculture machinery, maybe for manufacturing machineries, thermal appliances or heating solutions, whatever. Yeah. So you may have a certain approach now. You may have a certain approach. So considering everything, it is something like an overall achievement. It's very important. Okay, it is very important. Also, I can share with you one of the examples what I have experienced. I think you have heard about the gas scrubbers. Means when you have the polluted gas, you can use water to clean this gas. Maybe water can absorb the toxins and the dust and some other the pollutants. So I have done a calculation, very nice. I studied this, how to make it a very good design, and even I look into the design, the formulations, everything. Even I wrote a program and I have designed one. Then after design, I just look into the US Environmental Protection Authority. They also specified criteria. And when I try to comply that criteria also to incorporate with this design approach is no more valid. That criteria is the one we have to go through. Means it is something like inherently safe. Means 100% assures that the air pollution is prevented. So that's why. So sometimes the guidelines, sometimes the conditions, okay? Sometimes the design conditions, design guidelines, even there can be rules, and there can be one master point that overcomes everything. So my design effort, weeks long design effort goes, not to say wasted, but finally just one guideline command the solution. That is simple. Make it inherently, okay, non-hazardous, that engineering solution. So you may experience that kind of things. So I just came this into mind. This is in the year 2006. 2006 means now 15 years back experience. I just shared with you. Put a very big effort. Even I wrote the computer program. Even the simulation, even the minute, second by second, the air purification qualities, the program shows, but no choice. The final rule overrules everything. But good to know that, but there are this kind of situations, okay? This is fourth. So no time to look into all the 12, but We are solidly following this, okay, because it is so important, and this importance I no need to say, because it is self-convincing. I no need to say this is important, important, and very important. I no need to say. Once I explain it, yes, you naturally know that it is good to respect to this. That's why. That's how the knowledge should be. Okay, knowledge should itself explain and justify it. Yes. Item 5 now. It is something like before designing. In the design phase, you have to think about everything. Okay, you have to think about everything in this design phase. Okay, you have to think about all, even how would be the waste, how to prevent the waste. You should think upfront in the designs. So here it says, the fifth one, it is better to prevent waste than to treat or clean up waste after it is formed. That is what you call pollution prevention, because waste leads to pollution. Waste makes the things polluted. Things means the environment. So pollution prevention. Yes. It is part of the design goals. So when you prevent the pollution, your material efficiencies, your energy efficiencies, even your space efficiencies are higher. Means you are saving money. That is 3M principle, PPP. So it is better to prevent waste rather than to treat or clean up waste. Because once imagine your house waste, garbage, how struggling your parents sometimes. No place to throw the waste. See the Colombo municipal, this Mount Lavinia, the Hivala Mount Lavinia municipalities, the waste, the problem, even Ratmalana, your places in France, stinky bags hanging everywhere, dumping elsewhere, waste problem. So the best solution for the waste is prevention of waste generation. So that's why it should be in the solution up front. Okay. So it's better to prevent waste than to treat or clean up waste after it is formed. Because it is not only one time, repeatedly, daily, hourly, waste is being generated if the solution is not proper, not improper. So cleaning up is not one time, treating is not one time. It should be continuous. It's a huge burden, and it is it is quite costly. So prevention is important. Say, in your upfront of your design approach, you are thinking about this as well. See how nice this knowledge for you. Okay, this is number 5. Okay, the value of this explain itself, but you have to understand this. Okay, seems very valuable. That's why. Then comes the 6. See, the 5th one, Prevention instead of treatments, just 4 letters. Sorry, 4 words. Okay. Sixth, 2 words. It's not 3, not 1, it's 2. Maximize efficiency. Okay, that's why you have to respect the statement. Statement 6, the sixth principle is just simply with 2 words, maximize efficiency. Material efficiencies, energy efficiencies. Yes, see, it's the same. In the very first slide, I put this there. This one, products, process, and system should be designed to maximize efficiency. So this is item 6 really. Okay. That is one of the outcomes, even though I put it there. Because maximize efficiencies, almost all the 1 to 5 should be achieved. Yes. Without having targeted durability, you cannot maximize material and energy. Without this, you cannot maximize material and energy efficiency. Without minimizing diversity of materials, you cannot maximize the efficiency of material energy. Inherent rather than circumstantial. Without this, okay? Without this, you cannot maximize the efficiency. Yes, waste minimization. Definitely it's the maximize efficiency of material and energy. Sixth itself is an outcome of 1 to 5 plus some extra focuses. Products, process, and system should be designed to maximize mass, energy, space, and time efficiency. Yes, think about that. I just explained this to you. So later I will explain this afterward again. Mass efficiency, space efficiency, energy efficiency, time efficiency. So 4 efficiencies here. Okay. Matter means mass, energy, space, and time. Actually, there are more efficiencies. Yes. There could be even more efficiencies than this. Okay. Or effectiveness or efficiency. So this is very important. Now you know this. So let me put the 7th. Slowly coming to the manufacturing process and systems. See, from the design coming to manufacturing. Output pulled, okay, not input pushed. This says that one way meet the market, the volume need. Okay, so you are not producing excess, you are just producing the required one, but timely required volumes. So output means demand pulled. So what is market need? You produce it. So manufacturing based on planning. Okay, manufacturing based on planning. So that is very important. That is very important. Manufacturing based on plan. Okay. So I just add this one. I think no need to add. Yeah. So If no plan for manufacturing, you produce and you push it to the market. That's why we call input pushed. Okay, this is for the market. So your product, you into the market, actually you're pushing it to the market. Then you have to look into promotions and look for the markets. So you have you overproduced. Market is flooded with your products, and finally there maybe you need to take back whatever left in the market. Okay, the non-purchased one you have to take back. You don't know what to do for this excess manufactured products, excess volume. So that's why this is for already came to the manufacturing phase. Okay. So output based on the demand. Okay. I believe you can understand this. Okay. So this is the market focus. I just put here market based and produce the volume what the market demands. Okay. And not about producing the amount you need and push to the market. See, so that's why. Okay, so market based. I just put this our own words. Okay, so when it comes to manufacturing, even servicing, service sectors, industries, this is important. Okay, that's why you can see that sometimes the promoters, so-called promoters, yes, of course you have to promote your products well, but promote your products well, but there should be something based on the market demand, means the output is pulled by the market, output pulled, not we input something to the market and pushed. Yeah. So there is a good sense out of this. So this is the 7th. So it's about the manufacturing. So 1 to 7. So see, this is a very good, these principles if you follow with very good understanding, you have a very good discipline. You are well disciplined professional. Yeah, that's why it is very important. Yeah, even your market volume you can increase, you can have strategies and all. Okay, very nice. So the next one, 8th principle. So it is very important. 8th principle. This is related to manufacturing processes. Anyway, you need to consider this even in the design stages. Okay, we will try to understand this. So, design of products, processes, and systems. So, product design, then the process, and of course the system, maybe product systems, process systems, marketing systems, logistics systems, whatever. That's why you need little experience to think about this systems. Okay, this need a little experience to grasp more about systems. But all these three must include, let's see, integration and interconnectivity with available energy and material flows. Integration and interconnectivity, okay, with available energy and materials flows. Means in the process, in the systems, so energy is being used. So we consider energy flows. Even material also being used, processed, and all. So there are material flows. Okay. So there can be interconnectivity of the processes. Even there can be integration, means of course it is like maybe combining, okay, combining of the flows. Okay, example, maybe if one machine you can do two processes or more processes in one shot, or in just in few attempts, maybe just one machine use, maybe conducting many processes. So the machine's connectivity with energy and material, and this harnessing of energy and material is quite efficient. Okay, so here you have to think about this, integrating material and energy flows. So sometimes one part you make here, using the same material, another part you may be producing in 100-kilometer distance, another factory. So to bring those here, transfer materials there, so cost of energy, and even there can be waste of material. If you produce both at the same place, the waste can be minimized. So you can interpret this. Yes, interpretation is very important, and it needs, okay, it needs some exposure as well. Okay, yeah, even I just use the word interpreting somewhere, maybe interpreting. Okay, so I take out this because this one is not necessary, this slide. So interpreting, I did not put the word here, but I mentioned that interpretation of these 12 principles, it needs, and it is based on your exposure and knowledge. That's why. So I'm interpreting this, I'm explaining this based on my experience and knowledge. So when someone comes with more experience in different field, he or she may explain this with that exposure, and the interpretation may have similarities, but it can be wider scope with more depth. Or another one, maybe lesser experienced one, maybe he or she just put these words and just put the sentences, that's it. So that's why interpretation needs good exposure, knowledge. That is very important. So this is relative. Okay, relative. So let me go to ninth. Okay, ninth. So when you are designing, you can look into all these 12 principles. Yeah. Then your design is justified. Okay? Then your design is justified. Products, process and system should be designed. See, now you are talking about not only product design, process and systems. Should be designed for performance in a commercial afterlife. Okay? Commercial afterlife. How to say? Someone says cannot hear. Okay, yeah, let me try my best. So, commercial afterlife means, so sometimes the commercial, okay, performance in a commercial afterlife. Example, maybe passenger plane. After decommission for passenger transportation, it can be used for logistics. Commercial afterlife. Okay. Maybe one machinery used in one industry. Maybe if the precision's tolerance, there may be some deviations, maybe CNC machines even. It can be transferred into less precise, less precision level required industries. Okay, so commercial afterlife, especially for valuable machines. Even some, maybe some appliances even, or some solutions. So even after commercial life or commercial afterlife, this can be used for different purposes. So that is about recycling one way. Okay. Another way may be reusing. Yes, for different cases. Not refurbishing, but it's reusing. Possible. Okay, designed for commercial afterlife. Yeah. Example, sometimes you can see second-hand machineries and all. Okay. Even sometimes the vehicle sales, you can see we are using the Japan used cars. So for them, the commercial life is no more, but people are using it. Sometimes the big ships and all the aircrafts, you can see the similar commercial afterlives. Yeah. Okay. Rather than dismantling for parts recoveries. Okay. Parts and material recoveries. Instead of that, you can use it for different purposes. It's very innovative when you think of this in the designs. It is very nice. Okay. This is ninth. So 10th. So let me put it the 10th. 10th. It's reaching 3:30 now. 4 minutes. Renewable rather than depleting means your material and energy inputs. Renewable means those are somehow being regenerated, something like, let's example, wood. If you do the proper forest management, you can use wood as a raw material. Okay, it can be renewable, but fossil fuel, non-renewable. Okay, and depleting. So material and energy inputs, if it is renewable, it is very good. Wind energy, renewable. Today wind, tomorrow wind again. Okay, there is no any connectivity between yesterday wind and today wind. But yesterday fuel burn, today fuel burn, yes, both gone. That's how you see the renewable and non-renewable. So must use renewable material. Even I can see some companies, even German like high-tech companies, even many cases they use renewable material. Even in industry processes, you see wood as even in jigs and fixes. Sometimes you can see wooden pieces in the manufacturing processes. They are using because the principle is material, the wood is a good raw material, but nobody think about this. Instead of metal, some they use wood. Why not? Yeah. So there can be very good reasons behind those. So try to understand Putala design for separation is the 11th one. So let me put that as well. So the design for separation, of course, it is about disposing. You have to separate the materials and then use it back as raw material in the original forms. Separation and purification operations should be designed to minimize energy and consumption and material use. So this is number 11. I hope you have some understanding of this. And number 12, let me put it. Conserve complexity. Conserve complexity. This is about, okay, so I would put my interpretations maybe, but you can have your own experience. Future will have your own interpretations. Yes. So embedded means in the designs and all some complexities and even the entropy is related to some complexities, maybe some. It is different aspect, but you can see the embedded entropy and complexity must be viewed as an investment when making design choices on recycle, reuse, and beneficial dispositions. Yeah. So means the situational cases, complexity, there can be a possibility. Okay? Yeah. So, so because in some cases, even some complexities are possible. Okay, some complexities are possible. Okay, when it comes to the integrations and all. But still, we have to think about the recycling and reuse. That is very important. Embedded entropy and complexities must be viewed as an investment when making design choices on recycle and reuse. Yeah. Oh, there are possibilities really, complexities. Yeah. Conserve complexity. This is about. Okay. Yeah. Situation. So it is 3:30 Putta. Let me stop the class now. So if I summarize this, these 12 principles are well guided for design and manufacturing. Okay, in good environmental and eco practices. So this is very important to know this, understand this, and follow this when you get involved in the design manufacturing. And it mentioned about systems, products, process, and other systems even. Okay, so you go through this. So let me email this note to you as well. So this is everything about green engineering. If you follow 12 principles, you are almost done. So here, environmental aspects, something like, let's say, the global warming like aspects are not considered, but the hazardous and non-hazardous is concerned only. So I would say when it comes to industry, efficiencies and safety, okay, industry efficiencies and safety, and for the consumer's point of view, also material and energy efficiencies, and also for the product usage safety, these 12 principles are good enough and well guided. So other than this, there can be separate knowledge pieces we will be learning, and today we have no more time to discuss this. Greenhouse gases, please go through the previous video. So let me discuss about VOC in the coming week. VOC means the knowledge about volatile organic compounds. It's a very important knowledge that you should have. Okay, Buddha. So good day, and take care of everyone. Good luck to you all. So let me upload the video. So see you next week, and tomorrow we will be seeing the manufacturing and mechatronics for the sustainable consumption subject. Bye then, Putala. Okay, so let me start the class. Bye, Putala. Yeah, take care, all of you.